There are a few. There's like one over here. Okay. Thank you for your service to our country as we honor you today. So thank you all for coming. This is a great crowd. We know everybody's still meandering in as we try to get through registrations, but there's certainly a strong interest, there's a strong attendance, and we'd like to thank everyone who participated today, throughout the day, whether you're a speaker or whether you are attending. If you ask questions, thank you for being a part of this event. We would like to thank certainly the industry representatives here. There are more than 70 companies that are participating in some fashion today. So thank you everyone who's going to share some insights about your business and across a variety of domains that touch data analytics and data sciences. I'd like to thank all the representatives from different colleges, departments, and institutes at the University of Illinois. We have more than 20 in representation today. And I think that speaks to how this topic covers not just one particular area of the university, but truly an interdisciplinary topic that touches many aspects to make it successful. And hopefully we'll address those today through the variety of speakers that will be speaking both as faculty members and the students that are in participation as well. We would like to thank all the students that will be here today. There are even students coming on buses from other universities to be able to participate. So thank you for everyone that had an interest in this topic and wanted to be amongst the industry and faculty members here. To kick us off, I'm going to give you a quick little tour of the neighborhood that you're amongst. So in the last year since we were all together for the last Big Data Summit, there have been a lot of exciting developments in the research park, and I'd like to acknowledge some of the companies that have had successes or openings since we last got together. One of the biggest was certainly the opening of the new Yahoo building in the research park in the last year. That facility has more than 160 full-time employees in it and has continued to be one of the catalysts driving data sciences here in the research park. There's leadership in data pipelines, there's work in Hadoop, there's work in Flurry for new applications in mobile, there's new fraud detection work, and they continue to share many of their industry-leading practices amongst the research park. And we're so proud that they have chosen Champaign to grow their operations and to be their highest concentration of software engineers of any location that Yahoo has. In fact, in the last year, they awarded master inventors across the entire corporation that has more than 10,000 employees. 11 were honored with such a designation, and 3 came from here at the Champaign Yahoo operation, each with more than 30 patents to their name, truly speaking to the amount of work and innovation happening here in Champaign at Yahoo. And then immediately following that, we were honored to welcome many other companies that were also tapping into the expertise across our campus in computing and data sciences and computing areas that ranged from across different areas at the university where our students could provide expertise. And the next was the AbbVie Innovation Center, where they work on projects like data visualization that we'll hear about today. Next, we welcomed the Caterpillar Data Innovation Lab, where they're addressing new opportunities in their business, using business intelligence and looking at new technology areas that will change the way that they serve their customers, whether it's the Uberization that they spoke about recently that might impact their business, or how to use computer vision to get better analytics that can talk about the different job sites that they address with their equipment. Then we welcomed the Ameren Innovation Center, and we were so pleased to have the first utility and energy company join the research park. Many of you in the state of Illinois will have smart meters in your home because of millions of new meters that will be able to collect data and provide better information to this company and hopefully serve their customers with better energy efficiency and better intelligence. We then celebrated State Farm, one of our longest running operations in the research park, with their 10-year anniversary here in the research park. They've had more than 1,500 projects in the research park since they opened the State Farm Research and Development Center, many of which are some sort of data application areas, including applied statistics and more from a modernization standpoint, using algorithms coupled with drones to better be able to file claims and learn about incidents that need attention from the insurance market. And then we welcome Dow AgriSciences, which addresses a new and emerging area for them to be able to feed the world with better bioinformatics and better software as well. And we thank them for joining. That's Tim Hessinger, a proud alum of the University of Illinois, who's CEO of this company. We then just very recently welcomed the Capital One Illinois Digital Campus Lab. This lab will address areas such as cloud, data, mobile solutions to better serve their customers. And just this last Friday, we were very proud to have the ribbon cutting for Agrible, a company that is our fastest growing startup company, because startup companies and entrepreneurship are part of the fabric of what makes the research park successful and our community successful with entrepreneurs in our midst. This company is based on a firm roots in agronomy and agriculture expertise, and couples that with data sciences, atmospheric sciences, high performance computing to better serve growers throughout the US. All of this comes together in a peer community that we're so proud to be amongst. We have companies coming together to teach each other. We had Professor Robert Bruner, who was over here, teaching 3 data sciences short courses this last year with companies coming from across the park to learn together. We recently welcomed Professor Udata Pellikar to use data for better supply chain management, which we'll hear about this afternoon. And we bring everyone together with events like this and numerous ones throughout the year so that we can have this peer environment. And I'm very proud to say, amongst this peer environment, that we will welcome our newest company to the research park today. And that company is Granular, and Sid Gorham, the CEO, and he's right here, didn't see you earlier, I think is going to just share a little bit of their announcement that is being released today, and we'll be joining them to celebrate at 4:45 at Houlihan's after the conclusion of this event. We'll have a ribbon cutting event before then, and I'd just like to welcome him to the stage to say a few words about them joining the research park.
Okay. Thanks, Laura. So we're thrilled to be here. So we're a San Francisco-based company funded by Andreessen Horowitz and Google Ventures, and our mission is to use data science and software to make farming a more profitable and predictable business. So we're building software that allows farmers to run their business every day and make data-driven decisions. And we decided to open an office here in Research Park to get access to the talent that we need to build our business, principally in the area of software development and data science, but also in sales and customer support, because we're really looking for folks who come from, grew up on farms and understand farming, but also have an ag economics background and can partner with farmers as real business advisors. So this was a natural place for us to set up and to deepen our relationship with the ag econ faculty, and the collaboration opportunities there with students and faculty were really exciting to us. And the peer community that Laura was just describing is also very exciting. So thrilled to be part of the group, and please come join us for a cocktail or a beer after today's session. Thank you.
Thank you very much. Welcome to all our new friends from Granular, and thank you so much for choosing Champaign for your newest office. We're excited to have this company, and I think it speaks to the rise of agriculture and technology converging together, and there's a whole lot of that happening in the Research Park. We'll have a panel on that subject at 2:15 today. So, without further ado, I'm going to introduce our keynote speaker, but before I do so, I see some people that are standing in the back. We have chairs all the way up front. I see at least 15 or so chairs up front, so don't be shy, please take one. It's fine. If it says reserved, it's fine at this point. Go ahead and take your seats if you have not found one in the back of the room. So our keynote this morning, hey Laura, AV guy to switch the. So our keynote this morning is going to talk from Wolfram Alpha. Michael Trott is the chief scientist at Wolfram Alpha. Certainly from an entrepreneurship story, Wolfram is the best in Champaign. Say it's the most successful startup that doesn't refer to itself as a startup, but it not only grew out of this community, but remains here with hundreds of employees, many of which are brilliant mathematicians, brilliant data experts, and brilliant in computing. And today we're going to talk, as we start this morning, I'd mentioned an interdisciplinary nature of this topic that is data sciences or data analytics. And Wolfram Alpha really is an opportunity to look at the convergence of humanities and computing and data and how we can use that in a new way. So I'd please like if you could join me in welcoming Michael Trott to the stage from Wolfram Alpha. Thank you.
Good morning. Thanks for the nice introduction. So when I was asked to talk today at the Big Data Summit, I was wondering if I should talk about big data, how we deal with it in Wolfram Alpha, what kind of data we have, how they go together, how we keep them coherent, how we add new data, how we make sure they fit. But then I thought, maybe let's talk about something different that is a little bit more focused and a little bit much more basic, but at the same time, I was surprised how unexplored the topic was. I want to talk about what's the most beautiful proportion. So we all do visualizations, but the most naive question, what format should it be? Should it be 1:1? Should it be 1:1.6? Or what is really the best? So how did I come to this relatively esoteric topic? Around 2.5 years ago, we had a grant from the Sloan Foundation about building a prototype of a so-called computer archive of mathematics. Mathematics, as different from any other science, never goes out of fashion. What was written in 1780 is as correct as it was published last week. And interestingly, mathematicians really need access to this old knowledge. And a large majority of this old knowledge is only available in a scanned form, at best. Maybe it's just in some old paper that hasn't even been scanned. So there's been a big push to get more of this in digital form from Philippe Tondeur from the local math department when he was the head of the math part of NSF. And there's now a new push to make it really computable, get it in a form that the computer and the human can understand. So in that started, we had this grant about continued fraction as a subtopic. For instance, you can go now to the Wolfram Alpha website and say continued fractions about pi, and you get a large selection of continued fraction representation. And we will come back to why continued fraction matter for the golden ratio. So completely I want to speak paintings as data sets, something that is not very common but is very interesting, and especially in the last 1.5 years there have been a couple of very interesting results. Then I want to speak about the golden ratio, and after the golden ratio I want to speak, do we find it in paintings and what can we say about it? So if we have a look at big data in the natural science and in the industry are everywhere in 2015. If we go to Google, make a search, Google Scholar, we find in the order more than 100K hits of big data related publications. If we go to digital humanities, it comes already much less, maybe in the order of a few K, where most of them are analyzed of big texts, like what are all the common features of Danish fairy tales. There's been some very nice work done on this one. If we go to the visual arts, it becomes less and less. And if we are at paintings, we are in a 2-digit number at most. there are a couple of problems related to using paintings as data sets. It starts with generating the data. Most cases when we have big data, we generate them ourselves and we have a large amount of them. Here, we are totally dependent on art curators because they make them. Then there's the issue of copyright, which of course non-trivial. The quality of the data, we have no control at all. Whatever the art curators give us, we have to take. And then analyzing the data, some things are very easy. I will show some examples where we can do new things very quickly with modern technology. But some things are still out of reach, but I think many of them will become in reach within the next 1.5 years. So a couple of things that were really breakthroughs in the last few years with respect to applying big data type techniques to paintings. There's the work of Kim, Son, and Young from December last year, which was the first real large-scale quantitative analysis of paintings. And they analyzed around 30K of paintings, and they found actually quite a few interesting things, like a real quantification of how style changes over the last 500 years. And also worth mentioning is the work of Ingrid Debouchet. She invented wavelets, and she obviously uses wavelets. She has some research together with some mathematicians from Duke and art conservators in Netherlands about detecting forged paintings and how can you really make sure this is from this painter. Also restoring many of the paintings look 200, 300 years quite different. How do we get a few of the original back? And very much to the topic to be discussed today. Beginning of this year, in a Springer book, there was an article from Jensen where he said he took 200 paintings and photographs. Photographs, of course, a little bit not so ideal because many cameras come in a very well-defined aspect ratio, and he analyzed the aspect ratio. You got this relatively interesting curve. So we have for white paintings a maximum at around 0.8, then we have a small maximum at around square paintings, and then for tall ones at 1.24. So now, just a quick examples what we can do with modern techniques within the timescale of a day, if we have time, and say a half a day of computing time. A well-known law that we find everywhere in big data is Zipf's law. Frequently, Zipf's law doesn't just come in a normal form that we have just one slope, but many big data sets have two slopes. And very typical example is the Wikipedia word frequency. We quite clearly see a transition in the order of 10,000 points where the two slope changes. Other big data sets show exactly the same. And we can do exactly the same, say, for a big data painting. Say we try to get a high-res scan of, say, Mona Lisa. The best what I could find is 11 times 7K. And we see these two slopes quite nicely developed. And you can do this with many other paintings and you find exactly the same. And then you plot the average of a couple 10 paintings of this, and you see how this really changes over the last 500 years, which really has something to do with how styles change and how visual taste changed over the last 500 years. So another thing what we can do today, we have pretty advanced image processing today. It's pretty trivial nearly today to find the faces in a painting. So it's just this function find faces in the Wolfram language. So I took a couple paintings. Here's an example. And I say find faces, and it shows me where the faces are. And it shows me multiple faces. If there are not two abstract paintings, then of course modern technology still fails. So what happens if you do this with 10K paintings that you quickly download from Wikimedia, and you find this heat map? The paintings are pretty much symmetric, so left and right is not preferred, and the height of the maximum of the heat map is at 0.7, which is pretty much in agreement with the so-called rule of thirds in paintings, that the eye line should be at 2/3 from the bottom. So I saw a very nice paper I will show in a second. What about selfies? And it turns out most selfies are done incorrectly. You go to Google, make a quick image search for selfies from the U of I, you download 1,000 of them, you make the heat map, and you see it's clearly lower. It's at 0.63. And interesting, this has been observed globally, that selfies are you put yourself too much in the middle, put yourself a little bit up. This will look visually much better. So a last thing, what you can quickly do, painting popularities. Wikipedia has around 2,000 pages devoted to paintings, and Wikipedia access logs are freely available, but they are actually quite a big chunk of data. So we actually get them every day. We process them because we associate them with the relevant items for statistical purpose. So then you make this with the paintings, and you get this very nice zip flow again with an exponent of minus 0.8, pretty much exactly what you would expect for some average. And of course, the most famous painting in the world is the Mona Lisa, followed by the Scream, followed by the Last Supper. Also not unexpected. Then you can go into more detail. You can look what happens with concrete paintings and say the Scream, it was sold for 120 million. That it makes, of course, news. Everybody goes there. Then Warhol's version of it was sold. You see again a very nice spike. You can analyze the decay curves. There's a lot of interesting stuff one can do, but that's not the topic for today. Let's go to the golden ratio. It's a beautiful number, at least mathematicians like it. But if you look at it, it doesn't look actually so fantastic. It's 1 plus square root of 5 over 2. I mean, that doesn't look much better than 1 plus square root of 7. And if you look at the decimal expansion, that isn't the most beautiful thing either. It's more or less a random chain of digits, to the best of our knowledge. That's nothing different in base 2, 12, or whatever you like. But if you write it as a so-called regular continued fraction, that is pretty nice. It really gets better, you must admit this. So it's really a very nice representation. And it's base independent. And here comes the connection to the Sloan. We were collecting this continued fraction. There are vast generalizations of this, like this one, where we add something here. Then we get, say, 1, 2, 3, 4, 5. Then becomes a ratio of Bessel functions and much bigger generalizations. Visually, there are a whole slew of things that are present, or where the Gaussian ratio is present and that humans consider to be beautiful. The simplest one, you take a line to divide it in a bigger part and a smaller part, and the division is done by 1 over Gaussian ratio. Then there's the so-called golden rectangle. There's the so-called golden triangle. The golden triangle on its own is actually not so popular, but the two types of the golden triangle appear in a pentagon in various forms, and pentagons have been historically very important. Many paintings, you have seen these pictures where they draw 20 lines into a picture. They very frequently form pentagons. Then there's the so-called golden angle. We come back to this in a second. And there's the so-called golden spiral. And if you go to the complex plane, things become actually much more interesting. That's work that has been relatively late done, only in this century, by Schmidt. Continued fraction in the complex plane show a whole slew of new effects, and you get, for instance, very beautiful tessellations of the plane with circles. So one more thing from the math, then we're done with the mathematics. Then we only do statistics later. Fibonacci numbers, you all have heard about them. That's the problem with the bunnies, they get more and more. And if you form the ratio of successive Fibonacci numbers and you look at larger and larger of them, then you see this becomes the golden ratio. So here's this ratio, and if you look at the numeric values, you see here we are already basically at the golden ratio with no difference. And the eighth convergent, we will come back to this one later, which is 34 over 21, is only 0.6% off from the golden ratio. So differentiating when somebody uses two Fibonacci numbers versus when somebody uses really the golden ratio is a non-trivial question. Mathematicians really love the number, not just because there's 1 plus 1 plus 1, that's a little bit too naive. They have a property that's called, it's the maximal badly approximable irrational number. And there's some real deep mathematics into this. We don't want to go into this, but really it singles it out. So since when do people care about the golden ratio? It started all with Euclid, who the first time actually wrote it down, but he did not give it any special attention. He called it, it's the ratio by dividing a line in extreme and mean ratio. Doesn't sound particularly excited, and there's also no indication that he was particularly excited. Shortly before the year 1500, monk Luca Paciolo coined the term divine proportion. Then 100 years later, somebody calculated the first time the digits. In 1835, Martin Ohm, actually the brother of the Ohm from the Ohm's law in electricity, gave it the name golden ratio, originally golden Schnitt in German. And then in 1902, the current symbol phi, we come back to phi also in a second, was introduced. So why did he call it divine proportion? And he gave actually 5 reasons. Don't go through all of them. Like he said, it is unique, like God. It is done from 3 parts. the whole line and the two parts, like the Holy Trinity, and it cannot express in finite terms, so he already did understand there's some kind of special about it, it's a rational number. It is self-similar, like God, and it occurred in regular polyhedra, something that around 1500 many people were actually quite fascinated by. You remember these pictures of Dürer where they're always hanging some fancy polyhedra somewhere. And then he goes on and gives 13 effects of the divine proportion in a painting. What happens to you, some of the words don't have a good English translation, and it's actually very hard to pinpoint somebody to show concrete examples of what this means. So the next step towards the paintings is Gustav Theodor Fechner. He was a German scientist in the 19th century, and he did a lot of psychology from a very mathematical point from his time frame. He's best known for the Weber-Fechner law, meaning if you have some kind of external stimulus, say light or pain or temperature, then your pain is proportional to the logarithm of what comes in, not proportional to the actual quantity. And he wrote in 1876 a book called Vorschule der Ästhetik, Preschool to Aesthetics. You can get it from the Internet Archive in a high-resolution PDF form. Just want to show you 2 pages of it. Relevant for today's talk, he discussed 2 subjects. One being, what rectangles are the most beautiful for the human? So what he did is he cut out rectangles of various shapes and he showed it to a whole bunch of people and said, which one do you like most? And here I highlighted the one with 34/21, which we saw earlier, which is the 8th approximation of the golden ratio to Fibonacci numbers, was by far what people liked most. He wrote in his book. Then he said, if this is the case, I must be able to find evidence for this, so let me check this. Where would it matter most? Truly in paintings, because they are the most beautiful things in the world. So he went to a lot of effort for his time. He collected art catalogs from 22 European galleries. He transcribed everything he could find of them. So he collected data for around 11K images, and he gave his averages, medians, but unfortunately he didn't give any graphs that we saw in the beginning. And interestingly, the ratio where the maximum occurred and the medium was somewhere between 1.25 to 1.3. So he was actually a little bit disappointed that he couldn't find any evidence that the golden ratio really is used in paintings. So what about the golden ratio outside of mathematics? If you go to Google and look for scholarly papers, there are more than 10K scholarly papers. If you go to Amazon, you find more than 100 books. Most of them are not worth reading. And if you go to the internet, it's everywhere. But of course, one cannot believe everything one sees on the internet. And there are 2 persons, Frascari and Girardini, who wrote a very nice paper 15 years ago, basically saying, don't believe everything what you see about this. And he made this nice word, the faithful, where he replaced the F with the 5 from golden ratio to indicate these are the people who really believe in this. And the people who really believe in this, they see it in plants, in animals, everywhere in a human, in architecture. The UN picture, the UN building, it is really good, the golden ratio. In art and in plenty of commercial products. Like they point out, every single of the James Bond cars has plenty of golden ratios built in. So then, let's look who just started this. Fechner was actually not the first, but a couple years earlier, it started all with Adolf Zeising. He wrote a book, The New Science of the Proportion of the Human Bodies. And in this book, also available on the Internet Archive, he finds the golden ratio everywhere. You wouldn't believe where you find the golden ratio in yourself when you look at it. And a friend of him, a mathematician, said he confirmed all of this. There's little trace what he actually confirmed. So why do people think it is such a great number? And so the best and most quoted explanation today is the one, it is the most perfect way to divide something in a big part and a small part. So the biggest part is not too big and the small part is not too small, whatever this concretely means. So how does it look in the scholarly literature? Let's start with phyllotaxis. There is no question that phyllotaxis is governed by the golden ratio. Like, even in a simple cellular automata-like model, you easily get phyllotaxis out of it. But even if you solve nonlinear partial differential equation that model grows, you can show the properties clearly show phyllotaxis patterns with a golden ratio, golden angle as the increasing number. So this is all fine. Architecture. Things get a little bit not quite as convincing. It turns out that many of the famous buildings, like here in Florence, are actually not quite golden ratio, but they are maybe the third or fourth convergence of the Fibonacci numbers, meaning that they are rational, but they're clearly different. But okay, let's get this go through for now. Now, we would be surprised if you start looking where is the golden ratio in human beauty, and it's everywhere. You find plenty of proofs that beautiful Japanese actors clearly have the golden ratio, where not so beautiful people don't have it. If you look at detail, people add up to 1800 points on the human face, measure them, then they make all pairs of them. Of course, you find among this 2 million distances some that are the golden ratio. That's not very surprising. And there's a whole slew of pseudoscience. And very important also, good teeth have the golden ratio between them and the teeth itself. They also find it in mental beauty, so they did the following. They took some random things, 100, showed it to people and say, make 2 piles, one of nice things and one of not nice things. And they claim, interestingly, in most cases, people put in one pile 62% good ones, with 62% is 1 over golden ratio, plus minus. Where new research says it's not 62, it's 62.2. I have my strong doubts about these things. And also, in GATE, that's a very recent paper from this year. So if you walk, make sure that in 1 over golden ratio per fraction of the time your foot is on the earth, and in 1 minus 1 over golden ratio your foot is in the air. Then it looks most beautiful. And perfect stairs also, they made tests like ratio of height and width. It's most easy to walk if you walk on a golden stair, of course. And if you look at products, every good vacuum cleaner like a Dyson is of course built with the golden ratio, and every good iron and so on. There's a whole slew of pseudoscience out there. Then they make the experiment with some snack food. If it comes in a golden shaped package, it tastes much better, no question. This is not a joke, that's really a scientific paper from a couple of years ago. An old stone tool. What ratio does it have? Yes, golden ratio, plus minus percent, because it just lies so natural in hand. It's kind of an old form of an appliance, which we saw earlier. Then there's plenty in modern time. If you look at patents, you can get it to shape your eyebrow, or of course the acupuncture needle is the best if it comes in the golden ratio. And there are devices you can measure your own beauty if everything has the right distance. There's a so-called Fibonacci gauge where you can. And then modern time we have fMRI, we can look inside your brain, what happens if you see the golden ratio. So they show people pictures like this with slightly different proportions and say, so which one do you like most? And if the ratio is golden ratio, everything gets out of sync, they say, and clearly there's something special. And latest research, can you use it to unmask criminals? Yes, you let them write down a sentence, you compare with a normal human. The average height to width of a letter of a normal human is what? Golden ratio, of course. For criminals, it's at least a factor 2 of. I'm surprised that such things get published. Then there are also proofs of the golden ratio. Here's a very famous one. What does it mean to increase? Yeah, it means squaring. What does it mean to decrease? I subtracted. I equate the two things, and x squared equal 1 minus x is exactly the defining equation of the golden ratio. Okay, so obviously it sounds like not all of this can be true. That would be too good. So let's look what some skeptics say about this. And it started around 1965 that people said, no, this cannot be. That's not really to be expected that the golden ratio really appears everywhere. And there has been an increasing number of much more serious research on these things. And it turns out it's from time to time the golden ratio, but it's widely overstated. Like this classic example that you see of these old Greek temples, there's no golden ratio anywhere near them. Far, far away. Then Hungarian dentist said, okay, if this is really the case with the teeth, let's measure 10,000 for my patient. No, it's not the case. The average patient has a teeth ratio that's quite different from golden ratio. What about this facial things? So they really tried this, make faces in computer graphics and compared, and it's not the case. It looks quite different. Here's a very nice summary, recent one, which says, yes, there is something to it, but it's widely overstated and it's not so popular. So what about the Fechner experiment? Want to come back, where they showed people rectangles and say, choose the best one. So is it now true or is it not true? The experiment has been repeated more than 20 times over the last 150 years, and interestingly, there's still no convergence. Here's one experiment from 1898 where somebody, again, gave them rectangles, this time any form, and he made even a graph, like, do you like it most? And it turns out a little bit off from a square is a very nice shape, but then if it's the ratio 1 to 1.2, it's really ugly. It's get a negative score. Golden ratio, of course, gets again a good one. And the experiment has been repeated in a wide variety of things. Most cases they don't find it, some find it. Here is from last year a review of a meta-analysis of some of the experiments. And in around 2/3 they don't find confirmation. In 1/3 they do find confirmation that people like it. And now they also started doing the same experiments on rats and other animals. They also don't like the golden ratio. They like 1.2, pretty near to the painting sizes. Okay, so if it's not a golden ratio, what else could it be? And there are a variety of competing numbers that could be nice. It starts with Pythagoras. He was a big fan of ratios of triangles, edge lengths of triangles that have a right angle. And so the numbers that he favored was 4/3 and 5/4. Kepler was a big fan of this triangle which he built, where interestingly the golden ratio does appear, but he liked actually the square root most, which gives us 1.27, which is already much nearer to the 1.25 that we saw in many paintings. And over the last 30 years, probably by far the most common one has become the so-called plastic constant, also silver number, that architect in the late 20s invented, and it is indeed a nice number. He doesn't divide the line in 2 parts, he divides the line in 3 parts, so that all ratios that result have the same number. It's a very nice number, indeed. And it has been used for various architectures. There are a couple more which shouldn't concern us. So if we look how the rectangles actually look, so here is a set of them, and we see many of them are actually remarkably near to each other, but the golden ratio really sticks out. It's far wider, and it really sticks out to what many other scientists think is a beautiful number. So to recap, in mathematics, physics, chemistry, biology, there's no question the golden ratio is existent. In humans, maybe if you take enough humans, you definitely find it. If you take things that humans produce, some things obviously, but not all. So what about paintings? How does it look with paintings? And here is where, of course, the data starts. So that's a purely experimental question. Get enough of them, analyze, see what happens, and do people like paintings? So how do you get to this? So first you need some data. There are very few data sources out there that you can get. Many of them are only in the time or in the order of 100, maybe to 1,000 paintings. You have to go through catalogs. Some of the art museums and collections have some of their data online. Some art houses and some auction houses have records online. So the first simple thing is you could just take your cell phone out, ask Siri, and route it to Wolfram Alpha, and you ask for the aspect ratio, and you see some of the most famous paintings you might have heard of. Okay. One of the most famous paintings you might have heard of have an aspect ratio in the order of 1.2 or bigger, but again the golden ratio does not stand out. So we have around 3K paintings where we have all data available for, so we can look at them and see what happens, and we get a picture like this. The yellow line is the golden ratio, and we see the golden ratio is really not very prominent. Some other ones in the order of 1.2, 1.3 are there, and we see clearly various maxima resolved compared with the very first picture from Jensen from beginning of this year. So, and if we look at the cumulative ratio, it goes around 1.7, 1.8. One interesting thing is if we take the tall paintings. Sorry, I'm confused. I was saying I can speak 45 minutes. One interesting mathematical effect is if you take all tall paintings out there in the world and all white paintings and you convert them into each other just by using 1/, you get a distribution that is remarkably near to each other. If you make a quantile plot, actually it's really remarkable how they fit to each other. And the total number is also within percent order of magnitude the same. Now you can look about how does this fit with the various artistic movements. Maybe some kind of artistic movements preferred certain aspect ratios. And it turns out this is actually not the case. Virtually all artistic movements, give or take small variations, have the same distribution of the aspect ratios. You can look at individual painters that were productive enough to make enough paintings. It makes sense to make some statistics. And you find again 1.25 is a pretty good ratio, but not the golden ratio. If you look at modern painters, say here, Thomas Tinkate, painter of light, you find actually quite a different distribution. You see a gigantic maximum at 1.5 and at a couple other small rational numbers. If you look at ranges of aspect ratios by types of painting, again, some have pretty wide ranges, like allegorical paintings appear sometimes in a very wide form, but most are 1.3 give or take. You can relate to, does it matter if it relates to the area? And it's actually not the case, it does not relate to the area. What kind of genre and styles have the most extreme aspect ratio? And as a class, neoclassical nude paintings are the most wide ones because they typically lie, so it's around 1.8. So now let's look at some larger data sets to slowly come into big data. There's one good data set out in the world collected by two physicists from Hungary. It's a so-called Web Gallery of Art. They have 19K paintings, and we do the analysis again, and we see again nothing at this golden ratio, but we see a couple of well-resolved maxima between 1.2 and 1.3. And then we look at the active numbers and we see that the golden ratio actually did over the last 500 years not become popular. Actually the opposite, it became actually unpopular, whereas various small rational numbers became much more popular. And this has partially to do with the standardization of canvas sizes that started in France around 1750, but also with the taste and the perception of people. And if you look at this in a 3D plot, you clearly see how certain aspect ratio in the last 150 years really stick out and become much more prominent than any random one. Does it depend on the age of the painter, on when he painted it in his lifetime? No, it doesn't. It's pretty much the same. But if we look at the actual sizes of the paintings, we see something interesting. So these are not the ratio, these are the actual measurements, and we see this huge amount of small peaks. Again, because many of the painters, and Cézanne is for instance known for having explicitly emphasized this, like to just take the canvas as it comes and start painting, do no modification. And in the 2D plot you get then little islands of the various standardized painting sizes where the canvas comes from. The art collection in the world, virtually all collections have nearly the same average. There are a few very small collections that are a little bit biased. Now we can go back and redo the active factor analysis. Many of the old catalogs are today available in a PDF form. And then you can, okay, so I was told that my time is up, so I have to end this. Okay, I wanted to tell you a couple more things. Basically, as a summary, price does not, the aspect ratio does not depend on anything, and the golden ratio is really not the most popular one. The distribution of paintings is interestingly a Levy-Alva stable distribution. I'm not aware of any other man-made object that really has been proven to obey a Levy stable distribution. Then you have to deal with measurement errors, look at other things. One of the few things in the real world that do obey the golden ratio rule are French stamps. French stamps really are made to be beautiful. But many other things in the world do not obey this. So where do we go? So far we looked at the outside. We can of course hopefully in the next few years look in the inside. We can today, without problems, take a picture, identify what it is about. It's just one line of code. We cannot yet get all the things out, but hopefully in the next 1 or 2 years, we have the technology to take individual things out. And then we can look carefully at the composition inside the picture and see if we see the golden ratio somewhere inside. Okay, so the rest was a little bit abbreviated due to time reasons. Thank you very much.
Questions? I don't think we need this. Questions? Anyone? No questions? That's it.
Thank you.
What else? Thank you, Michael.